cerca de, Mufasa de alrededor. Oh, I didn't realize it was recording. Okay, well, here's the video I promised from last week's recitation, the last week recitation. So here we go. I'll upload this to YouTube and send out the notes after I finish recording this.
So oxidation versus reduction. So the reason why this is important in metal chemistry, especially transition metal chemistry, is that basically every single step you have within the reaction is going to either be an oxidation or reduction. And just to go over those definitions, loss of electrons means it's oxidation, and gain of electrons means it's reduced. The little mnemonic to remember that is Leo, the lion, says grr. Applying it to a member of this recitation section is Ethan, the Robert, says gar. So what?
Actually, I know another one.
Oil rig?
I was taught
Don't do that. That's useless.
oil rig is the same thing.
You can use whatever one you think is better. I don't care which one you use, but I would prefer you use this one. So what? Because it's the one I learned. It's knowledge. I don't need to defend the truth. So, in terms of organic chemistry reactions, or organic reactions, not applying it to metals, it means chemical. Applying it to chemical reactions when we're looking at some just random compound, and we're usually analyzing a specific atom within that molecule, usually carbon or some metal like rhodium, RH. So the compound or the atom we are looking at will, if it's oxidized, if it goes through an oxidation reaction, a more electronegative element will attach, causing it to lose electrons, hence it getting oxidized. And if we're talking about reduction, it's exactly the opposite. A less electronegative element is added. So how does that work? Someone asked me how that works. Well, thank you. Thank you. Is that Brian? Thank you, Brian. You get an A. There might be extra credit if you come to the concert tonight. So a common reduction mechanism is hydrogenation. So we take this, we have carbon. I'm just going to look at these two carbons right here. We've got carbon, hydrogen, hydrogen, and then carbon, hydrogen, carbon, just like that. When we add the two hydrogens across, making it just a straight up alkene. Oh wait, we need to talk about the electronegativity difference first. Yeah. I'll send these notes out and a video of them if you want. So here we've got carbon, carbon. If it's the same electronegativity, it doesn't make a difference. H1 has an electronegativity of about 2.1 and carbon 2.5. So if it goes in the direction of the most electronegative atom. So with respect to this hydrogen, we say, okay, well, it's donating one of its electrons. This hydrogen is also donating one of its electrons. When we add both hydrogens across, we have C, C, H, H, H. Again, the CH bond or the CC bond is not making any difference because carbon and carbon are both the same electronegativities. But here, we've just added an extra hydrogen. So this is 2.1, 2.1, 2.1, 2.5. Now we've got an extra electron coming in because of the extra carbon-hydrogen bond. So in general, the rule with most organic reactions, if it's a reduction, we add hydrogen or remove oxygen. Now let's talk about an oxidation. So an oxidation looks like this. So we start with an aldehyde, and I'm just going to write O means it gets oxidized. What it is, we don't care as long as it gets us where we need to go. So in the first one, when it's an aldehyde, again, we'll consider just this carbon right here. Whoops. We'll consider the carbonyl compound, carbon that's in the middle. And so we've got carbon, carbon, oxygen, oxygen, hydrogen. So again, carbon-carbon does nothing, but what does the oxygen do? It's a lot bigger. I think it's 3. Carbon, oxygen, yep, it's 3. So here, when we look at this one, with each of the oxygen bonds, we say that it's pulling away 2 electrons because it's more electronegative than carbon. And with hydrogen, again, it's just going to donate its 1 electron. So here we say the state is -1. We should probably go over oxidation states. But then when we oxidize it to an acetic acid, we got rid of this hydrogen right here and replace it with an oxygen. So now we'll draw it out again. Carbon, carbon, oxygen, oxygen, oxygen. Now for each of these oxygen bonds, we have essentially removed 3 electrons from the carbon. Yeah. So we assign electrons based on the electronegativity. So the more electronegative element is taking the electrons, right? That means we subtract 1 from the thing it's attached to. For every single bond, we subtract 1 electron. So here we subtract 2, but we add 1 because of the hydrogen.
So even though typically when you lose an electron, you get a positive charge in this case.
Let's see. So it's negative. Let's see. So it's -2 gained plus. No. It's -1 electron gained minus 2 electrons lost. Gained. So yes, this would be a +1, meaning it has a net loss of 1 electron. And this would just be 3 because we've got 3 oxygen carbon bonds. So this oxidation number would be +3. And then going back to this, so reduction in general, we are adding hydrogen or removing oxygen or some other electronegative element. If we apply it to oxidation, it's exactly the same, just the opposite. So in oxidation, we generally remove hydrogen or we add oxygen. And it can just be an H, it doesn't have to be H2 or O2, it just has to, it can just be one atom of such. So is this starting to come together more clearly? So the reason why this is important in metal reactions or reactions involving metal catalysts is it will help us track where the electrons are going and how we can, or how the overall reaction is occurring. So let's see. Man, these notes are very blurry. Okay, let's go over the Monsanto process he briefly mentioned. And given that he talked a lot about it during class, I would imagine this is probably going to be a test question. I wouldn't be surprised if it isn't a question, then I'm just like whatever. If it is a question, then don't be surprised. So either way, don't act surprised. By the way, most of the points lost on exams are just not reading directions clearly. So by the way, Monsanto is modern Hitler, just corporized. Yeah, that's a weird mustache. But the reason why this is interesting is because it uses a very reactive element, carbon monoxide. Carbon monoxide. Remember, this is the gas that if you breathe, you die at very low concentrations. So some chemist was probably smart enough to say, hey, how can we get this to stop killing us and start helping us? So this, yeah. Oh, and we need water in there as well. The reason why carbon monoxide is highly reactive is because it's got a negative charge on that carbon atom. So it's like a carbanion. Its overall charge is 0, but this is the best structure we can make in order to stabilize it. So yeah, don't breathe this, but use it to make acetic acid. And of course, this catalyst, metal catalysts are actually pretty common, but the catalyst we're going to use is rhodium in the middle with the 2 iodines attached, and carbon monoxide and carbon monoxide. That's what we're going to use. Now the first thing we want to do with any transition metal complex is we want to identify its location in the periodic table. And we want to know what the overall charge of the complex is. So the overall charge of this complex is just 0. So a rule about metal complexes is that
Actually, the overall charge is -1, as you can see in this shaded area right there.
there's really no one atom that holds the full positive or negative charge. It's just kind of floating out there somewhere. We really can't draw resonance structures for this, at least nothing that can help us terribly much. But the way to determine, let's see. So I want to get where it is in the periodic table. Let's look that up really quick. Whoa. So rhodium is 45. Oh, that's not a helpful table. We want to get we really want the group number before. I want the column number right here. That'll tell us how many electrons it's going to have. So rhodium lands right there. So it's got 9 electrons that we're concerned about. And this is something that's really important, that when we're going with the periodic table is we're going to fill the d orbitals before the s orbitals. So jumping back there really quick. So we saw that it has 9 electrons. So this is the 4d position. We fill in the 4d before we fill in the 4s. So what does that look like? So we've got 4d. It's got 5 orbitals in it. That's something you just need to know. So we know it has 9 electrons, so we just go 1, 2, 3, 4, 5. Then we start filling it up. 2, or 6, 7, 8, 9. And we have nothing in the 4s2. If we moved a couple elements down, so if we went to silver, then we start occupying those 4s2. But the thing you want to take away from this is that we want to fill in the D's before the S's. Die before survive. It's just a mnemonic I just came up. He uses that word so wrong. He uses that word wrong all the time. Like, oh, here's a nice little mnemonic. Mnemonic is a memory trick you use to help you remember something. So like this will help you remember to fill the d orbitals in before the s orbitals. He's using it as a concept, which is completely wrong. But anyway, so we see that we've got 9 electrons of interest, but notice how many are unpaired. Just one right there, right? So really, we only care about that 1 electron right there. Wait, is that the case? I think it is. Two bonds? Not in this reaction, though. So yeah. So because it has this 1 unpaired electron, and these other 8 are paired up, this lone electron right here will give it an oxidation state of +1. So we have that 1 lone electron right there, and it's still neutrally charged overall because all of the because it hasn't lost any electrons, it's just donated them. Another way we could do the oxidation number is to take off groups. So remove the groups. So if we take that rhodium example, we could take off rhodium, we can make it iodide minus, C minus, O plus, C minus, O plus. So that's where we're talking about the neutral versus positive. If it's negative, the group that is, the ligand, it's taking away an electron. And if it's neutral, nothing happens. And if it's positive, then it will donate an electron. So here we've got 2 negatives. So that's taking away an electron. That's taking away an electron. Oh. This is supposed to be minus. This overall complex is actually -1. Sorry about that. Maybe not. And so the neutral elements do nothing. So rhodium right here, because it's lost 2 electrons, its state is +2. +2 for its oxidation state. Now let's go through the reaction, shall we? So the first thing that happens is SN2. I think, did a lot of people miss this question on the test? The fourth one? So the first thing that happens is, rhodium has a pair of shared electrons it can donate to CH3 iodine. That's a good leaving group. Iodine comes off. What's the element forming that reaction is rhodium with 3 I's on it, and wait, no, sorry, it's the methyl. It's adding the methyl group on there, at least for now. Now let's again determine the oxidation number that came from adding that methyl group onto it. So the iodine, so it becomes iodide, that's -1. Iodine becomes iodide, that's -1. Carbon monoxide is neutral, doesn't do anything. What about the methyl group? What charge does it have if we were to take it off? No. Good guess, but not quite. It is negative. So they're taking away 3 electrons. What's its oxidation number? Yes, +3. Good job, guys. So because this is, let's see, because this is becoming more electron deficient, it's going to make it more apt for this iodine to come in, which by the way has an oxidation number of -1. So because this rhodium is losing electrons in a sense, well, not really losing, it's just distributing it to other atoms, the iodine will be able to go, aha, sling in right there, and we're all happy. We're actually looking back at our orbital molecule, we see that we have this 4D orbital, something we can use to pair with another atom or group, and the force 2 right here gives that place for the Lewis base electrons. So we always come back to the molecular orbital theory. Even though you guys hate it so much, it's actually quite useful. I'm not saying that you really do hate it, but you know, whatever. You do? That's good. Okay, so the next thing that happens is this. So now we have rhodium attached to 3 iodides, and it really doesn't matter what order you attach them in, it's all the same thing. Got methyl. There's something. Now let me draw out the CO in a more detailed way. Whoops, O plus and C. Yeah, that's still plus. This carbon is now an excellent electrophile. Because it's triple bonded to oxygen, it's got a ton of electrons getting pulled away from it. Does that make sense? So what can happen next is that this methyl group, or the bond between the rhodium and the methyl group, can just attach to that carbon right there. So this pair of electrons between the rhodium and the carbon will just come off and drop onto the rhodium, like so. Okay, what do we have next? I'm going to have to go down here.
Actually, it's the other way, where the method, the electrons right here in this bond will still attach to the carbon, but instead of the electrons dropping onto the rhodium, a pair of pi electrons will pop up onto the oxygen instead.
I'm running out of room. So we've got rhodium, 3 I's. now we have CO, and aha, look at that. This is where our acetic acid is going to come from. Or rather, at least it's the beginnings of such. Remember that we still have carbon monoxide floating around in the solution. I didn't draw that up there. We need that in order to make the reaction go forward, because in the next step, carbon monoxide, which again is a highly reactive species, it'll be like, aha, rhodium is missing another ligand, because ideally it would like to have 6, but whatever. Just add on right there. So the new component we get is RH with 3 I's again attached to it. Got the acetate. And now we've got 2 carbon monoxide groups on top of it. Let me think what I'm trying to do. Now the reason why this is significant is now we can bring this pair of electrons from the iodide down and again attack the carbonyl, which is again an excellent electrophile. So we come down here. Oops, wrong way. So the product we get is RH, I, CO, and CO, and oh, look at that. We just regenerated our catalyst. Regenerate catalyst. So that means we are back at our oxidation number of -2 for the rhodium. And we get something that is close. That's the final product of this reaction. Now, what seems familiar about this particular compound? What is this compound? Aha, yeah. Acyl halide, which again is highly reactive, right? So in order to turn it into acetic acid, we can just take methoxide, be like, wee, pump it up, bump it back down, jump off the hydrogen, and we get our, oh wait, no, we want hydroxide if we want acetic acid. Like so. Now it's OH. And there we go. Something he briefly mentioned at the end was the OXO process.